Great. Good afternoon. We're the Missouri University of Science and Technology Human Powered Vehicle Design Team. I'm the president, John Bowers.
I'm the lead engineer, Garrison Key.
First, we'd like to talk to you about our design this year for our trike Leviathan.
If you want to refer to some more of the in-depth details in the design report, but we made several updates to the design since then. One in particular being a doubled-up locking mechanism. And in our locking mechanism for our trike, we had one single plate. We put two plates in there that attach to the shocks, so that way the axle is loaded in a shear stress rather than a bending stress. We also limited the lean of our trike to 30 degrees, so that way if the person was to dump it over, they could easily shimmy their way back up. In addition, we were limited in how much we cut into the side of the fairing because of our A-arm sticking out the side. So we limited to 30 degrees for those purposes. Also, we changed our locking mechanism from a pin design, which you saw in the design report, to a hydraulic brake caliper. So we used a really beefy four-piston brake caliper that held on to a rotor that is connected to the trinary link that is the locking mechanism. Also, some critical portions in the design I would like to mention are the importance of true center point steering for our particular design and the innovation. As you can see here, center point steering is simply the kingpin inclination of the knuckle, so that way it determines where the wheel turns about. You want that to be right in the center of the wheel. We created true center point steering, which is where it's infinitely, no matter what lean angle, always at the center point of that wheel. So you have smooth lean. We had a head bubble for our fairing, which was a very large, a very important aerodynamic decision. We did it for the sake of visibility because we chose to have an adjustable seat. And so in having an adjustable seat, we needed to account for the different head positions of the riders. It was much better to use a head bubble to do that. We did an advanced power measurement this year. We took a power tap hub, which is capable of measuring the power and cadence and torque and whatnot speed of the riders under certain tests. We created several different tests, which you can refer to in the design report. And we created rider models. And this is very important because we had a trike, it was fairly large, we knew there was going to be fast bikes in competition. Also, we wanted to ensure that there was good performance from the riders, so we wanted to be able to calibrate for those different riders. And in doing so, we created these models for fatigue and whatnot under different circumstances to ensure the person could have maximum performance.
Now we'd like to talk to you about our innovation. Right here you can see a little bit of leaning right there on a curb, just as a slight example. But for our innovation this year, we decided to do a hybrid handling system, or HHS, which fits in the innovations criteria for the dynamic ride systems area. This is a group innovation of leaning capability and independent suspension. So basically what it is it allows the stability of a trike at low speeds, however you can still lean and take turns as a bike at high speeds. Also, with the independent suspension, this allows us to go over most terrain. So right here is a video that we have of the leaning capabilities of our trike. And then up next, this is testing the independent suspension. And this is a 5-inch curve that he's going over right now.
You can play that one.
I do this all the time.
He really does.
There we go. All right, so the design of the innovation was really the majority of the design for the vehicle. There was two major sections that we really had to integrate together, and that's the leaning portion of the leaning steering and the independent suspension of the innovation. What marries the two is actually a patentable idea in the locking mechanism that we designed, to have the suspension, the leaning, the Ackerman compensated steering all in one. So in the lean steering, it's created by two simple parallelogram geometries. You just have two different sets of A-arms, and that allows for rotation about the center of the frame. Pretty simple, it's been done. We put in the locking mechanism to ensure that at low speed we can lock it up, keep it upright, you can steer it like a trike, and also when you disengage it, you can lean and it feels just like a bike. It requires that true kingpin inclination. I mentioned this earlier in the design as a critical point. And the importance of that is we had to create carbon fiber hub wheels. So that way we could stick the knuckle inside of that wheel. And in doing so, we make the knuckle and the kingpin one. And we are able to have continuous center point steering. And in doing so, it allows for very smooth transition between leaning and upright trikes. So that was very important. Also, the Ackerman controlled steering maintains its Ackerman compensation throughout the whole entire leaning process. And the way we did this is we ensured the instantaneous axes of the dual drag link arms remain in the same plane. That was very difficult. And then we'd have the independent suspension. We tied the independent suspension in to the A-arms to the locking mechanism. And in doing so, whenever we lock the locking mechanism, this is the old style with the slots and pin on the prototype. This connects to this trinary link, which is grounded to the frame. And when you lock it, you still can allow for movement in the A-arms based upon what the shocks move. But when you unlock it, you can lean it, and then you can also have the independent suspension still. If you do look at most designs, the shocks are grounded to the frame, and if you were to lock it at a leaning angle, you would have no suspension because it would be locked to your frame. So that's the patentable idea that we've been looking into, talking with our school about going through. Our suspension, we designed to have up to 4 inches of travel, and the reason why we did this is because we can also change the wheel sizes we stick on it. There's 18-inch rims on the front and 22-inch rims we could stick on the rear, and it'll increase the chassis height, and also the wheels that you can put on them are like hybrid. They're between mountain and road, so you can have much better handling off-road or rougher terrain like gravel. Also, we took into account the amount of travel in the shock, the linearity, and other things like heat. To test these, we built 2 prototypes. First prototype is simply to test the steering, lean steer mechanism. It worked very well. We had to make a few tweaks with how robust the A-arms were and how well aligned they were, but that was it. We put it through the standard tests of simulating the course and whatnot, and it passed. So then we went on to prototype 2, which was integrating the suspension system, which is where all the innovation was really in line. We tested it by running it through several different speed bumps, as you saw. Excuse me. And it passed as well. We learned a few things, which I'll cover in the next slide. As you can see, the steering, we had to fix our tolerances. You had to make sure the tolerances were very tight on the A-arms, and there was no deflection in those A-arms whatsoever. We really wanted to reduce weight, but we had to ensure that there was absolute rigidity, or else things could get squirrely. Also, we had to make sure the tolerances in the steering were nice and tight, no hysteresis, so that way our riders would have an easier time controlling it. We also reinforced the locking mechanism, which I discussed, big 4-piston caliper, extra plate. Also the suspension, I discussed briefly too. We looked into things like body roll, which we figured was somewhat negated whenever you leaned it, because it doesn't really squat out whenever you lean. So, but if you rode it like an upright trike, you will get body roll at high turns. Shock calibration, essentially figured out which ratio we wanted through kind of an estimate based upon what it was designed for on a mountain bike, and also the forces that it would undergo. And then we used a modular type movement of the shock to figure out what position it was best in for the performance we wanted. We were able to calibrate it to the proper squat and whatnot. If we were to continue this design, as you can see, I would really recommend we find out how to make this thing lean further without sacrificing the fairing or whatnot. There's quite a few decisions into that. We've considered actually covering the wheels and whatnot. There's quite a few aerodynamic reasons why we didn't, but we would want to increase that lean angle. Also, overall weight. We made it fairly robust, factor safety of 2, fatigue life. I'm glad we did, according to the West Coast. But we could have reduced the weight, increased the overall performance. Also, I want to continue power testing and see how we can make that drivetrain more efficient. We were able to create proper rider models, but I'd like to compare it with other drivetrains by measuring the power of the cranks and whatnot to continue to increase the power transfer.
So as Garrison said, there are many things that we would like to continue to work on. I mean, this is our project, our baby. We want to make it absolutely perfect. However, we were very proud of the vehicle that we did come to competition with, and we were very excited to race it again. Is there any questions?
Yeah, we machined the Venisal 4 foam of the actual shape of it into a tooling foam mold, and then we were able to suck it down the Venisal on top of a tooling foam block, and then make the outer shape, flip it over, stick it inside the mold, apply a vacuum to hold it down while it machined the other side. So then therefore we had our mold, which can fit inside of our core that could fit inside of a rim. And then we had a hub that was a 2-piece hub. One side you inserted through here, and the other part you pressed in on the other side. And then we had pin nuts pressed into the foam. I actually forgot to mention that. And they would sit into it and allow you to thread into the core material with aluminum that was bonded to the core. And then we would lay up the carbon over each side of it, vacuum it down, and then sand it down, make sure it looked all nice. And then on the other side, you can't really see it, but there's a plate that screws onto the other side that was pressed in, similarly to how you screw in through the disc, the rotor, and to the side.
Yeah.
So that was quite a process.
Yeah, I don't know. What's the length ratio of your shop?
41. So we have 1 inch of travel in the shock, 4 inches of travel.
Did you investigate or what you're using for crushing your ground? Like, did you do anything outside standard to adjust for that length ratio, or?
Essentially, all we did due to time constraints is we considered what it was designed for, looked at the linearity, and we looked at the ratio that they used, and we considered the amount of forces that it would undergo, came up with an approximate estimation, and then did trial on the prototype, so we could knock it out as quickly as possible. And then considered for a few basic concepts and suspension.
Did you do any testing where you were lean steering and would hit a bump? How does the suspension actuate under that? Just out of curiosity.
It works great. Matter of fact, whenever we were leaning